In the microscopic world of atoms, the nucleus houses protons and neutrons, while electrons orbit in energy levels. Inside the nucleus, protons and neutrons are composed of even smaller particles called quarks, held together by glues. These interactions are governed by fundamental force, where the strong force binds quarks. Electromagnetic force influences charged particles like electrons. The weak force plays a role in radioactive decay, and gravity affects macroscopic objects.
So let's move on to the theory. In 1911, Ernest Rutherford said that atoms have tiny, dense, positively charged nucleus, where electrons move around the nucleus. However, Rutherford can't explain why electron doesn't collapse into the nucleus despite losing its energy. So in 1913, Niels Bohr improved Ernest Rutherford model by saying that electrons move in quantized discrete energy level. So the electron emit or absorb energy when transitioning between levels. And then in 1920s, Erwin Schrödinger stated that electrons actually do not have definite orbits. Its location described by a wave function that represents the probability distribution of their location. So next is the quantum mechanics principle of the atom. So the wave-particle duality, which is discovered by de Broglie, the electron act as both waves and particles. This means that they have properties of both particles and wave, which helps explain their behavior in different situations. Well, next is the Pauli exclusion principle. This principle states that no two electrons in an atom can have the same set of 4 quantum numbers. This explains the unique arrangement of electrons in an atom and helps to determine the chemical properties of an element. Lastly is the Heisenberg uncertainty principle. This principle states that we cannot simultaneously know the exact position and momentum of an electron. The more accurately we know one, the less accurately we can know the other.
So now we move on to the significance of atomic structure. Firstly, chemical behavior. The atomic structure determines the chemical properties of an element, including its reactivity, bonding behavior, and placement in the periodic table. Secondly, material properties. Conductivity, hardness, melting points are influenced by their atomic structure. For technological innovation, semiconductors, nanotechnology, and quantum computing relies heavily on an understanding of atomic structure. Manipulating atoms and their arrangement enable the creation of smaller, faster, and more efficient devices.
First application is in laser technology. They enable precise medical procedures and high-speed communication. Next, medical imaging. This relies on X-ray absorption variants in tissues, aids in diagnosing and treating ailments. Last but not least, radiation therapy. Using ionizing radiation to target cancer cells showcase how this principle benefits healthcare. Understanding atomic structure not only depends our knowledge but also drives innovation, leading to technologies that enhance our lives.
Understanding how atoms interact helps in assessing the nutritional value of macronutrients and micronutrients as well as their absorption by the body. In transportation, atomic structure is important to select materials that enhance vehicle fuel efficiency. For instance, the atomic arrangement of materials like aluminum alloys or carbon fiber composites determine their strength, weight, and thermal conductivity. Lightweight materials reduce vehicle mass, which decreases the energy required for acceleration and maintaining speed. This results in improved fuel economy and reduced emissions. In conclusion, atomic structure at the particle level is not only fundamental to scientific understanding, but also essential to the advancement of technology and everyday applications.